Okay, I'm Jack Rickard of EVTV, and we have just taken delivery of our brand new Tesla Model 3. We're probably, according to Bloomberg, about the 7,000th car delivered, and all but 17 of those new Model 3 owners has put up a YouTube video giving their first impressions of the car. The 17 are kind of, all of them are sort of alt-left, libtard, Trump denialists, so I can't be seen among them. So I have to do a YouTube video giving my first impressions. I promise not to show you the frunk or the hatchback. Let's see. But beyond that, it'll be a standard Model 3 discussion. I ordered the car in the first 15 minutes of when they took online reservations on March 31st, 2016, and I picked it up February 19th at 1:30 p.m. appointment in their delivery center in St. Louis, Missouri, about 125 miles from here. We drove up in the Model S, and Richard drove the Model S back, and I drove the Model 3. I'm here with Marius at the Tesla Delivery Center in St. Louis, Missouri, and taking delivery of a new Model 3.
Yeah, very excited. What do you think of it?
I love it. It's the same color and everything as my Model S.
Yeah.
How long have you worked at Tesla?
About 2 years.
How many of these have you introduced into the world? You're like kind of the obstetrician for Tesla here?
Yeah, quite a few here in St. Louis.
You do delivery of the babies?
Yeah, getting to everybody that, very, very lovely people I work with, so everyone's excited to get the cars and get in them, start driving them, so yeah.
So yeah, that was my next question, is people coming in to get them, what kind of attitude are you getting from them?
Very excited. It's currently mostly owners, so I had a Model S or X, so everybody's getting their third or fourth car or second car, so they're kind of familiar with controls, so it's very, very fun process.
Part of the Church of Tesla already.
Yeah, for sure. Yeah. Just upgrading or, getting a little bit of wide for the kids or something like that.
And how long have you worked for Tesla?
About 2 years.
2 years?
Yeah.
And how do you like that?
Very, very awesome. Yeah, great company.
Is that right?
Yeah, especially right now.
Pretty exciting.
Yeah.
Okay, Marius, well thanks. We're here to picking up the Model 3, and I'm delighted.
Yeah, awesome.
Thank you so much for your help and making it a good experience.
Yeah, of course.
And so I've got some impressions of its handling on the highway primarily. The car costs $56,000. Of course, they're selling the fully loaded long-range versions right now. And I got a little bit of a bump because I was a Model S owner. I actually reserved 2. That only applies to 1 reservation. And so I got this. I got it in the same color and the same wheels as the Model S. And so they look very similar when styling about town. There's some very good news, and I think some very bad news about this car. And so let's talk a little bit about that. It has 15.4-inch display sort of centered in the dash. It's a good display. It operates quicker than the one in the Model S. It's apparently got a faster microprocessor in it, and it's very crisp. And they have some interesting features that they've added. More on that later. The basic drivetrain is a 192 kilowatt motor. It does 317 foot-pounds of torque, and it'll accelerate this car from 0 to 60 in 5.1 seconds. My other one is a P85 Plus, 350 kilowatt motor, a heavier car, and it'll do, I think it's rated at 4.2 seconds. So there's no shortage of power in this car. unless you're a racing enthusiast, it doesn't matter. Has a 75 kilowatt hour battery in it. They have a 60 kilowatt hour battery, but they're not selling any of those. They're kind of maximizing their pricing. Again, the Model S was originally announced with a base price of $55,000. My P85 cost $107,000 delivered. This one was supposed to be a $35,000 base price car, and this vehicle cost $56,300. I think somewhat excessive for what it is. Basically, it's intended by Mr. Holzhausen, the designer, to be sort of mano a mano with a BMW 3 Series. And so, and I think they succeeded at that. The drive down, I would say in some ways I was quite disappointed. It is a smaller car, 3,814 pounds, as opposed to 4,731 on the Model S. And it doesn't have the air suspension, and it feels like a smaller car. In fact, the suspension felt cheap to me, a little bit bouncy. And I think that there is a huge opening there for one of you suspension tuners, since it doesn't have the ride raising and lowering and so forth of the Model S. You should be able to put other suspension components on this car and get away with it, and it could use them. I would pay for them. It did not feel good to me. The steering has 3 modes: sport, standard, and comfort. None of them had any comfort. And in fact, the car is twitchy. Staying in my own lane was an issue, particularly exacerbated by one of the fatal flaws of the car. I didn't think this would matter much. It does to me. The display, while it's interesting, is not the 17-inch Model S display, but missing is the instrument cluster. And what you get in place of that is 2, maybe 5/8-inch numerals on the center display showing your speed, and 2-point type for the PRND mode, and a state of charge bar that you would need the magnifiers I use to look at PC boards to see it all. The problem with that was an enraging cruise control. In the last 10 years, I've probably spent $10,000 a year on personal computers, desktop computers. I still haven't gone over completely to phones and tablets. I need a PC. I would say about $800 of that went to Microsoft because I don't do Windows. And it's not that I don't do Windows because it's slow and stupid, and it's not because after 20 years Windows still can't find a COM port. I can forgive all that. Bill Gates somehow got it in his head that it was okay to suggest or to tell me what I ought to be doing with my computer, when I should update it, and whether I really, really, really wanted to close that program without saving, or whatever his little advisories are. I started programming in 1979. As I say, I've been waiting for something to load, something to save, or something to print for, 40 years, near enough, 39 years. I tell computers what to do, and they don't tell me what to do. However, after having a thorough briefing by Marius at Tesla, a very pleasant young man and a very pleasant pickup experience. I kind of failed to find out how to put on the cruise control. And I fooled with this and with the center screen, and was probably very nearly killed, I would say 6 or 7 times, departing my lane, dicking around with the center screen. I finally pulled over in Ozora and pulled up a YouTube video and found out that cruise control is very simple. You simply pull down the PRND stalk past D to hold, and that will hold your current speed in cruise, and I think that's great. So I pulled back out of Ozora and went down the highway, and I tried to do that, and it didn't work. Now, again, it's in 2-point micro type on the screen, but if you magnify it enough and you bend over far enough, you will be able to read right before you whack into the Freightliner that cruise is not available because the driver doesn't have his seatbelt on. I don't need Elon Musk or his cars to tell me when and where to wear a seatbelt, and I strongly resent him implying that he would know better than I do about how I ought to drive the car. By the time I got to Perryville, this car was pretty much for sale. And by the time I got to Fruitland, I'm thinking, we could have an auction at EVTV starting at $1, and I bet I could get rid of it pretty quick. I've kind of calmed down. There are some things I do like about the car, but that isn't any of them. And the display, frankly, sucks. It would be great to use as a tablet in bed. It doesn't belong in a freaking car at all. None of it. And it certainly is a safety threat when driving down the road to look over to check your speed. Since I couldn't put it in cruise control, I had to manually maintain my speed, but I've got no speedometer in my line of sight. So I have to look over to get the speed from those 2 little black numerals on that display. And I consider it a nearly fatal flaw of the car, or maybe it's an opportunity. We're going to work on a solution to that. We're going to take a look at that a little bit more in the future. It does have a coefficient of drag of 0.23, and I thought that was interesting. It's not that much smaller than a Model S. It's 184.8 inches long. My Model S is 195.9. That's 11.1 inches. On the width, it's 76.1 instead of 77.3. That's 1.2 inches. I can't find that. On the height, it's 56.8 instead of 56.5. It's actually 0.3 inches higher. But they do something. I guess the sill is lowered because the dimension from the ground to the roof, I just about can't get into a Model 3, and this actually works. I can get in this car. I also like the door handles. The other ones pop out sometimes, sometimes not. It depends on where I have the fob in my pocket. If it's behind the pocket knife and under the flashlight, I can't even get in my Model S. If I rearrange it where it's out in front of the pocket knife and above the flashlight, then they pop right open. And that's the fob. More on that in a minute. These, you just press them in, and they do kind of electrically open. And similarly, when you're in it, there's a little button here you push, and it kind of pops open. There is a more normal door handle down here so you can manually open it. I like all of that, and I particularly like the increased height. The other thing is they have rearranged the interior. You lose probably a foot out of the frunk, which in the Model S, I've already used just since 2013. I've used that frunk probably 4 times, so I don't miss the loss of space. The hatchback has plenty of space, probably more than the Model S in some ways. You can fold down the back seats on this and haul lumber in it. But in taking out the frunk, they've moved the whole dashboard down and forward. And you have a much bigger windshield, there are about 2.5 acres of dash to pile stuff on, old cigarette cartons and Kentucky Fried Chicken boxes and stuff. Well, imagine my delight. So that's the kind of stuff I live with. So a lot of room there, but my point is the car feels lower in front of you, and you have better visibility. Everybody tells me they think they're sitting up higher. You're not. The front of the car is lower, and that opens up your view. Excellent, excellent design in that respect. So I do like that. The interior is very Spartan and clean. I would be a fanboy, but they've taken it too far. When he announced the car, I assumed they were going to put in a heads-up display. I don't know if it was too expensive or took too long to develop or what, but their panel display, it doesn't cut it. Everybody has an opinion of that. I don't have an opinion. It doesn't work. That's not how you drive a car. It's dangerous to drive this car depending on that panel for information. I departed my lane 6 or 7 times, at one point almost into a truck. So that's bad news all the way around. The the charging port has been redesigned. It pops up instead of sideways. When you press the button on the thing, that works fine. You do not have to manually close it. When you get in the car, it just closes itself. And that's going to cause some problems. People are going to try to manually close it and probably dick up the little motors and stuff. But I'm delighted with it as an improvement. I've actually been stopped by the police, who I think wanted to take a look at my Model S over the, I'm always driving around with the charge port door open. My favorite feature is actually the fob. It's gone. I don't like this fob. In fact, I don't like or approve of car keys for the last 15 or 20 years. I do not believe it appropriate that I have to pay $375 to get a duplicate car key to start my car. Not that I've ever lost any keys, and I know that you all have never lost any keys, but who came up with that scam? And we've actually got this going on with the fob. You can buy another fob, you got to take it to Tesla to get it married to your car. Another 300 and something bucks. It has buttons all over it. I keep it in my pocket. Again, with the pocket knife, the flashlight, and a couple of PC boards, some capacitors, and a frog. Okay? So if I sit down, I'm pressing this button. The car is a mile away. But I'm draining the coin battery in it to the point where I get about a month on a coin battery for this fob. And I'm terrified, of course, of losing it. And so it's, I don't like the fob. I don't like regular car keys. And they have actually come up with a solution to this. This is my little passport that I get with the car, and it has 2 Tesla credit cards in it. Actually, they're not credit cards. They're an NFC, or near field communication card. Near field communications has been trying to get off the ground for about 4 years now. It never quite gets there, but the concept is really good. It does information transfer, but it doesn't do it where everybody in the grocery store can receive it. You have to be within 1.6 inches by spec to read it. So to open the car, you put the card right here. And to drive the car, you have to put the card in a very specific position on the center console. More on the center console in a minute. This looks like a huge step backwards. It's not. This is your key to independence. The car will not only operate and open from NFC communications from these cards, but it will operate by Bluetooth Low Energy from your phone and your Tesla app. And what you have to do is bring up your already existing Tesla app, or you can download it and link it to your Tesla account on the Tesla website. And by holding this on the console to start the car, you can key your phone and that app, but most importantly, your phone to the car. And I did my phone and my wife's phone in about a minute and a half. Now, you may not have the fob with you, and you may not know where your car keys are, but you do know where your cell phone is, and you're always carrying it. I'm getting to be a big fan of phone apps to open things and close things and start things, because I am going to have the phone. And I probably use a smartphone less than anybody you know. For me, it's a stopwatch, a calculator, and does a couple of other things. I don't talk on the phone hardly at all. As many of our viewers know, send me an email, let me think about it, draft a reply, and send it to you. They call here all the time thinking they want to talk to me. In almost every case, by the end of the conversation, they realize they never did want to talk to me. I'm not a pleasant person to talk to, and I don't have any answers for them anyway, because I don't know the answer to their question. If they'll send me an email, I can think about it, I can research it, I can look back and see what we did in fact do, and what the price is and what its capabilities are, and perhaps frame a cogent reply. But if you call me on the phone, I don't know anything. I can't remember what I did know and I'm supposed to know, and I'm really a crabby old man. You don't want to talk to me at all. So I don't use the phone that much, but I do approve of it in the case of opening garage doors and cars. And what has happened is your car key is now your phone, and if you lose your phone, change your phone, get a new phone, this is how you get to program it yourself. You don't have to go to Tesla or Toyota or Nissan to get a key registered and keyed to your car. You do it yourself with this little card. So keep the cards. That's how you reprogram your car keys, and your car keys are your phone. A brilliant solution all the way around. What else do I like? The center console is brilliant. The guy wired up a couple of plugs for my phone. It has 3 sections, really 4. There's a forward section that you can flip up and park your phone and actually plug it in to charge. And it's not that you plug in a cable. It's got a little thing like a charger. You just seat the phone on it. It has a center section you can flip up. it's big enough you could probably move Hooterville into that section. It looks little, but it's deep and wide, and it can hold. You can pretty much move using that. I've never met a connector I liked, and I got to tell you, I never met a cup holder I liked either. And they've got two. They're in exactly the right position, and they're exactly the right size. And I just absolutely love them. And then you've got the usual flip-up center console right under your arm. So the Model S had no center console, and the Model 3 has the best one I've ever had in a car, bar none. It's the most comfortable, the most effective, and the thing is just drop dead, shiny black, gorgeous. And so I really like the center console. What else? Some minor things. The navigator. Most of the functions are kind of like Siri, voice input controlled. And so you can press a button on the steering wheel and say, navigate Cape Girardeau, Missouri. And it takes where you're at and navigates to Cape Girardeau, Missouri. And you can say, navigate to somewhere else. You can bring up the nav map, punch a button, and get all the superchargers within 500 miles in a list. Pick it off the list, and it'll calculate the route for you. Navigation is excellent. That's what the center display should be doing. I don't mind it having setup functions like creep and so forth, but it's not a driving instrument. It shouldn't be referred to as a driving instrument. You shouldn't drive referring to it, and it's a horrendous safety violation the way they've got it set up. And you need something to tell your basic modes, your basic cruise, and your basic speed without looking down at that. A heads-up display would be nice. Gauges would be nice, but you can't really improve on the instrument cluster that the Tesla Model S had. It was great. It ought to be on this car. I can't believe it's that much more expense. The ventilation vents go all the way across the dash, and you can adjust them up and down and left and right. The stereo and the climate control, superb. Superb. So the only key that this is a cheaper car, I think it's got kind of a chintzy suspension and steering system. I think they made an egregious error on the instrumentation. And beyond that, it's a 1,000-pound lighter car. It's not going to glide on the freeway like the Tesla Model S. Top speed of 140 miles an hour, 5.1 seconds 0 to 60. That 192 kilowatts is overkill. You do not need a four-wheel drive unless you want to race this thing. It's plenty perky, plenty of acceleration, quiet, and a 310-mile range. That's a longer range than I have on my Model S. In fact, I fully charged the Model S. We drove it up there 125 miles, charged it for about 40 minutes on a regular charger at the Tesla service center, which oddly doesn't have a supercharge station. And Richard had 4% left when he pulled into the shop. It was a near miss. And that's a 250-mile round trip on what's supposed to be a 275-mile car that we charged for 40 minutes while we were there. And so, again, the range and capacity of these batteries is subject to a little bit of marketing hyperbole. That said, it's still a good range, and you can still do a whole lot with the cars, and certainly in a local sense. On balance, I am delighted with the car and enraged at Tesla. That's a camel under the nose. That's how Bill Gates started. And that cruise control needs a software update tonight. and they need to get off that stuff. But they're becoming increasingly control freaks about their car. I find I am unable to get onto service.teslamotors.com. Recall that's the system they put up to comply with Massachusetts law. It appears to be disabled, and they are not in compliance with that law at this point. Worse, 2 automobile manufacturer associations have launched a vicious fight against right to repair legislation across the land, and they have done so by enlisting the manufacturers to make repair data available to you to avoid the laws. Well, now that's a little bit circular. Why would they mind the law if they're going to provide the data anyway? That's your first hint. But Tesla didn't join either one of them. And so the free and open source concept that Elon Musk espouses online has become control freak beyond. His only competition there is John Deere with control issues over the operation of the vehicle. And as we demonstrate every day, it does absolutely no good at all. It can only slow things down and prevent us from having much competition, but we do have competition. The diagnostics port is gone, and there is a new one where the OBD port, right in underneath the dash, right inside the door, used to be. There is no OBD2 port on the vehicle, and I think that may be not in compliance with the law in some states. But apparently, as a zero emissions car, it's perhaps not required anymore. But it's unfortunate because there's a lot of OBD2 instrumentation in the aftermarket that won't work on this car, which so badly needs some sort of aftermarket instrumentation. There is a diagnostics port. I don't really know what it is yet. It's a little 5-pin sort of white plastic port. 4 pins are populated. I would love to think it's ground 12 volts and can high and low. More likely 100 base T Ethernet. But it's a very unusual connector. It's actually not a very unusual connector. It's a pretty common one. It's just a very unusual one to see in this application. And so we still have to investigate what's on those pins and how we can access it. But I'm betting I can find a CAN bus in this car somewhere and get wired up to it. And so again, control freakitis, you're going to lose. We'll find a way in. So a lot of good news and some bad news. Overall, you're not driving a Model S. He has successfully differentiated his product. I think that might be ameliorated a little bit with some suspension components. So there's an aftermarket opportunity there. Not by me. I don't know and don't understand suspension tuner guys. They practice the black art, and I'm not familiar with it. But they are, and it's a popular thing to do, and it could certainly, this car could certainly benefit from that. The rear seat, how would I know? I'm never going to ride in the rear seat. It has a rear seat. For kids, it'd be fine. If you want to drive around with 5 adults, you got too many friends. You need to get rid of a few. You could do it, but it's going to be pretty tight. The rear hatch, plenty of room for whatever you need to haul. The front is handy, you know, for little items, but as I say, I've used the one in the Model S about 4 times ever, so who cares? And the car really isn't that much smaller. It's 1,000 pounds lighter, a foot shorter, and but it feels like a smaller, kind of dancier car, and so it is not a Model S. Model S is still the king as far as I'm concerned. But beyond that, it's a great car. I think they're going to sell a lot of them. I'd like to see them, come out with the 60 kilowatt battery and so forth. I'm not sure you'll ever see it. People are going to want the 75, and $56,000 is not $35,000. I'm sorry. The upgrades we got had to do with the autopilot and so forth. So far, I haven't gotten the summon to work. I haven't gotten the thing to work. I can tell you my Model S can open the garage door about 1 time out of 3. And if I voice request a song, it'll get the right one about 1 out of 4. And so my interest in autopilot and auto drive is waning fast. I think we're a long way away, and you need to show me you can open a freaking garage door and play a song on the radio before we discuss what all you're going to do about driving me down the road. I certainly don't want to summon my car, have it drive through a closed garage door, then open the door and go park in front of the neighbor's house. And that's kind of my experience with Tesla's software and automation so far. I'm underwhelmed. The paint and the finish, a lot of people are over critiquing the gaps and so forth. The paint job is great. They've got a great paint shop apparently, and so I don't have any complaints there. So it's a good car. It is fun to drive. There are some issues, but I think over time they're solvable, and but may call for some aftermarket people to jump in and make some hay when they're building a $500,000 cars in their first full year of production. It certainly leaves an area of opportunity there. So that's my quick take on the, which of course, as everything in EVTV videos, is neither quick nor can you just take it. You've got to suffer through it like we do, 4 hours to get the goods. But that's my unqualified, but nonetheless strongly held opinions initially, and I reserved the right to extend and revise my comments into the congressional record. This is the first day with the car, and I've gotten used to things in the past. So stay with us. There'll be more about the Tesla Model 3. Here, I thought I'd show you. This is our browser with a service called Time Is, and it gives me my local time. This is a cool terminal program that is connected to an EVTV DUI, and this is the Arduino program showing the ESP32 board. And as you can see, I brought that up. I searched for Wi-Fi, SSID, River House, that's the house I'm in, connected, and got a time mark. And let's see if we can cut that loose. And you can see here we're sending and receiving CAN messages on the ESP32 as we are on the EVTV DUI. And in fact, they're connected to each other. So the ESP32 prototype board we have connected to my local AP access point here at River House. Gotten a NIST time mark, corrected our hardware clock by that, and gotten off. And now we're simply getting a time from our very excellent hardware clocks in this board. And we kind of then process that to send out CAN messages over a pair of wires that are about 6 inches long to our EVTV Dewey, and it receives a CAN message ID 707 that has some data in it and decodes that and prints it to the screen as our UTC time, and it sends some messages 107 back, and those are received over here by the ESP32. So we went and got a time mark, set up our hardware clock to be fairly accurate, and then we're passing it over CAN to another board and then displaying it on the screen. And you can see we're at UTC 21, 9 p.m., 33 minutes and 39 seconds. Our local time is 03, shown here, 3 p.m. in the afternoon, 33 minutes and 49 seconds. We're UTC -6, and I'm showing UTC time here. I don't care anything about local time. And so, but what's amazing is you can sit here and watch the seconds change between here and here, and we're pretty much, I'd call it dead nuts on. And so that's kind of interesting. We'll go through all that processing and it not really matter. Let me show you our setup here. We've got our two boards. The one on the left is the EVTV Dewey, CAN Dewey we call it. It's a clone of an Arduino Dewey with a couple of differences. It has an EEPROM chip added. We've taken off one of the USB ports and replaced the other one with kind of a more robust micro B printer port. They're simply physically the little micro USB ports they had on there would break off on eye contact, and these just keep me from fumbling them off with my club fingers. And we have 4 screw terminals replacing the barrel jack for 12 volts and providing 2 terminals for CAN high and low. And we have a single CAN channel on it, and we use that board for everything. It's a controller for a Chevy Volt charger, Chevy Volt DC to DC, Delphi DC to DC, Chinese TCCH chargers, the Eberspacher heater. We just use that for everything. In fact, it's the heart of our Tesla controller for the full pack and for the modules. It has a shield that we had to do for that, but it's that's the controller board. And on the right is our prototype, complete with some very fine micro wiring changes that Colin had to install. And this is our first prototype of the same board. Basically, we've lost the end row of pins because we need it for the antenna on this wireless device, and an extra CAN port. We put on a micro chip MCP 2515 CAN port. The ESP32 has a native CAN port in it. It needs a transceiver, and we provided that with a little TISN65 transceiver chip, but we wanted to add a second CAN port while we were diddling around with it, and we did, using the MCP 2515. We're not going to use that ultimately. We've already decided, since we have to redo the prototype, we're going to go to a new CAN fast data chip. It's backward compatible, still does CAN, but it's supposed to be the next generation of CAN that'll be showing up on cars in 2019 and 2020 with a much faster data rate. And so we'll have that chip on the board here. Right now, we're connected to the CAN 0, the native CAN on the tin silicate chip through the TI transceiver, and that right now is giving us the best performance. There was a library by Thomas Barth out there that did very, very basic stuff. These guys haven't gotten too much into filters and masks and stuff, I'm spoiled rotten by Colin's Can Dewey, and so he's in can hell right now, trying to come up with a way to come up with one um, can library that will handle both the native, put a wrapper on Tom Barth's work, and add to it filters and masks and callbacks where you can. We have it where if you receive a certain message, it will send you an interrupt, and you'll have an interrupt service routine in your code to handle that particular message. And I'm spoiled to death by this. It's actually how I met Colin, was when the Recharge guys did the first Arduino Mega board with CAN on it, and we kind of started collaborating on a library for it, and Colin pretty much took it over and left me in the dust and came back with something that was great. We've used DeWiCan for years. Now he's got a lot on his table to give us a second CAN port and kind of do a wrap on the existing work on the ESP32 internal CAN port, and make it all look and act the same with the same filters and masks and callbacks or interrupts used on the two of them. So that's what we're playing with today. And as you can see on the screen, it's working pretty good. We have data going back and forth between the two boards. We're displaying time, and I can put it up on the screen and check it, and it's running pretty close to what we want to do. So let's take a look at the code, and I'll show you a little bit what's going on. As I say, this is still very much a work in progress, but I'm having some success this Sunday afternoon. Okay, let's talk a little bit about our code. I get a lot of questions about CAN. We're getting a lot of calls from people who want to learn about CAN. I don't quite know how to tell them. It does involve some programming, and many of them are loath to get into that. But we're going to start talking a little bit about some of the techniques. And this is a pretty basic program that's going to get time from our using the network time protocol, NTP, and send it out the port onto the CAN bus. And we're going to test that we can send and receive frames. And as I say, we're doing this to a EVTV CAN Dewey that just has a little CAN skeleton program on it. It receives the messages and decodes them and sends a message for us to receive. Let's see. The first thing we do is our template, and this is a little object declaring it so I can do streaming at the serial port. We've talked about that before. This is a global variable loop time that I use for some other things. We'll get to that. And then we have a series of includes. ESP task WTDTH. If you'll recall, I did a segment on watchdog timers. You can find it on YouTube. We're going to have watchdog timer. We're going to include ESP32 underscore can.h. That is our ESP32 CAN library that Colin Kidder is developing for us. He had done a library called CAN Dewey years ago that we've used a tremendous amount, and I think it's what's put us out ahead of most of the world with regards to automotive CAN is really his library that lets us do CAN much more easily than most people, and it's and better and faster, much faster. And then we have, we're including TOD.h. I recently did a video on using the wired Wi-Fi in the ESP32 chip to log on to your local access point and send a UDP, user datagram protocol packet to the network time protocol server in Boulder, Colorado at NIST. And that gets us a time mark, and then we correct, in a sense, our hardware clock locally in the ESP32 so that we can get real time. And this is becoming increasingly important in some of our applications having to do with solar and peak shaving and so forth. So the first thing I do is instantiate an object. I'm going to call it RTC for real-time clock using TOD, which just stands for time of day. This doesn't do any calendar functions. It just does time of day since midnight in universal coordinated time. And then I'm going to declare two variables of type can frame, an out frame and a frame. I could call this an in frame, but I just call it a frame. So these are two variables, but they're not integers, they're not floats, they're not booleans, they're can frames. And can frame is a new variable type given to me by ESP32.can. And if I make a variable, it's actually held in memory, sort of by the library, and I can write to it and read from it, but it's just going to pass me the address of it. That's how it's going to pass data back and forth to my various functions. And that really, that structure, that variable type is the key to a lot of things with what Colin's doing, and it's what I like so much about his work on CAN drivers. I'm going to put this up here. This is a structure. This gets in a little bit deep, but just we can have objects. We can also just have structures. And we're going to make one, and we're going to call it can frame. And this is a structured variable that contains a lot of things. Think of it as a little form you fill out. If you're going to send a CAN message, you need to fill out the form, and then you need to send it. And if you receive a CAN message, it's in a form, and you can read from it. But you have to know what all the blanks on the form are for, and that's what this is. So it's type can frame, and the structure has a 32-bit unsigned integer for ID. That's where our message ID goes. 32-bit integer for FID, which is family ID, which you don't really need very much. 8-bit integer for a remote transmission request. You just have to make sure that's set to 0, as I found out today. A 8-bit integer for priority. It's only important for transmitted frames and then only for special uses. We have a 8-bit flag for extended. Extended indicates that we're using 29-bit IDs instead of 11-bit. And length is an 8-bit integer that holds the number of bytes that will be in our data. And finally, we have a thing called data that's of type bytes union. Well, that's another structure, and it's really the key to this. This is all header information. We're not going to talk about a lot of it. The important parts are ID. That's what we deal with messages about, whether it's extended or not, and the length. Time, priority, RTR, and FID, we almost never have any use for it at all. They're provided in the CAN specification, but we just haven't found them to be terribly useful. But we do need the ID, the length, and whether or not we're using extended message IDs. And then we have our data. That's in the structure right after length. And but it's not really defined here. It's in another structure. And that is a very interesting structure. It's an unsigned 64-bit variable, and we're going to call that value. And within it, it has a structure that is two 32-bit variables, low and high. And alternative to that, it has four 16-bit variables, S0, S1, S2, and S3. And alternative to that, it has 8-bit bytes. And alternative to that is, if you don't want to call them bytes, you can just call it byte. And what this lets us do is refer to our CAN frame by name, which is in frame or frame or out frame in our case, and dot ID or frame dot length or frame dot extended. But we can also refer to our 8 data bytes as frame dot value. And we could store, for example, a 64-bit floating point number in frame dot value. And when we're on the other end, we can simply retrieve it as a 64-bit floating point number. And it makes it very easy to put big variables in and out. Alternatively, we could store two 32-bit integers by calling it frame dot low and frame dot high. Or we could use four 16-bit variables, frame dot S0 or frame dot S3. It would actually be frame data dot value, frame dot data dot low, frame dot data dot high, frame dot data dot S0, frame dot data dot S3, or we could say frame data byte and an index of 1 through 8, or 0 through 7. And so there's a variety of different things we might want to put in a CAN message. Calling structure here lets us do any of it kind of very quickly. And we don't have to break a 32-bit byte into its constituent low byte, and the next low byte, and then the next low byte, and then finally the highest byte. We could simply say the variable Jack's 32-bit, we want to set frame dot data dot low to the 32-bit integer Jack's data. And similarly, we could do 16, and in fact, you can combine them. We could put a 32-bit variable in low. Now we know that that takes up the same space as S0 and S1, but then we could set two 16-bit variables in S2 and S3. Or we could have a 32-bit variable in data.low, and we could have a 16-bit variable in data.S2, and we could have two 8-bit variables in data.byte 6 and data.byte 7. And so you can actually load up your CAN frame with some remarkable ways by becoming familiar with this structure, and I'll show you how that works here in a little bit. So we've declared two of those frames, and they're very important. This is some declarations. They don't do anything. They're for some functions I have later, and I don't know why I have them here. You don't normally have to do that in an Arduino program, and for most of my functions you don't have to do it, but I get an error, and if I'll do a declaration up here, it goes away. There's something amiss with the ESP32 core for Arduino, I suspect. And here's some more globals. debug equals true. I'm going to use that to turn on and off whether I print out the can frames as I send them and receive them or not. Last has to do with some timing we're going to do when we print can frames. Loop count is for our loop, and TOD valid. False is a time of day valid. When we go out to our access point and get the time structure, sometimes we fail, and I can check TOD valid to tell if we failed. Here's two character strings. One contains the station set identifier, and one contains the password for my access point here in my house. And let's go right into setup, and I think this will show you what's going on. First thing I do is set my serial to begin at 115,200. That sets up my USB port, so I can I can get a display, I can enter things if I wanted. We just use it to display data and observe the program. The second one is if RTC. Now remember, that's my object name for my time of day class. Object is RTC. So I'm going to say if RTC.begin and the SSID and the password from up here, then set time of day valid true. This does a whole lot. This does the whole process of going out to the access point and polling for an NTP and correcting our clock is all done right here on this line. And if it returns a 0, it means that it's not valid. We didn't complete it successfully, and we would not set this to true, and we set it to false up here, so we're going to be without time of day. This we've covered in an earlier video on watchdogs. We're going to initialize our task watchdog for 4 seconds, and it's going to print some panic information if it goes off, and we're going to add it to subscribe this task for the watchdog, and then we're going to initialize can. And more on that in just a second. Let's take a look at our loop. The loop is pretty simple. We're going to set a timer. We're going to feed our watchdog. Remember, we have to give it a reset once in a while or it goes off and reboots us. We're going to call a function to send our 707 can frame, message ID 707. And we're going to check how much time we spend in this loop, and we're going to print that to the screen. And that's all we do. The only thing I'd like you to note here is that we did nothing in this loop to check for incoming can messages, and we don't have to. And now I'm going to show you why. Here, the last thing in our setup was initialize can, and here it is. We're going to say if can.begin 500,000. The CAN bus and different devices operate at different data rates. Many of the Chinese chargers operate at 250K. Most things in a car operate at 500K. That's why you may want to have 2 CAN ports, and why we're working so hard to get into the ESP32 DUI, the EVTV ESP32 CAN DUI board. So here we set our data rate, and then we're going to talk about filters and callbacks. Apple talks about callbacks. A lot of people call things callbacks. In my day, they were interrupts and interrupt service routines. I am still somewhat resistant to this term, but we're going to use it because Apple says so. And so the first thing we're going to do is set an RX filter, and we're going to name that filter 0, and it's a filter on message number 110. and our mask is 0x7FF. Now, what that means is that all the bits have to match this address of any incoming message, or we're not going to do anything with it in this filter. False means that we're not talking about extended 29-bit addresses. We're just dealing with 11-bit. Now, we can deal with 29, but we have to set that to true and do a bigger mask. If we set this, let's say, to 0x7F0, then we would be able to accept in this filter any message from 110 to 119, because we're masking off the last character with a 0. If we set it to 0x700, we're masking off both the trailing bits, and any 100 series message would pass the filter. And then we're going to set a callback, and the callback is going to be on this filter. Anything that gets through that filter, we're going to send the frame directly to a function called handle can frame, which we'll talk about in a little bit. But the important thing to note here is that we're setting up a filter to trap messages of message ID 110. And it's important to understand this masking. It's a simple ORing, and at 7FF, all the digits, all the bits of the ID are passed. Anything I set to 0 here doesn't pass. And so, for example, I can set this to 0FF, and any 10 message, a 110, a 210, a 310, a 410 would all pass this filter. And so it's a simple OR of this with the message to get a result to check if it passes the filter or not. So that's what I was talking about, filters and masks. We're going to filter out everything but this, and we're going to mask that to make this more powerful, what we can do. And this is where the magic happens. We're setting an interrupt, really. And if we get one of those messages in, we will halt the operation of this loop or anything else we're doing in this program. And we will jump to, we'll save our stack and everything and jump to handle can frame and go exercise whatever's in there that we want to do, usually to decode message number 110 and take the values out of it and put it in some variables. I'm not doing that in this little code demo, but that's what you put in there, is extractions and with the scales and corrections, offsets for data you're extracting from your can messages would be done in handle can frame. And the next filter does 120. And so the way I've got this set up with the mask, it has to be those exact messages. And so you can set up a different handler for each of these. I happen to have just made them all handle can frame because I don't want to clunk up the code with a whole bunch of different handlers. But that is how I would normally do it, is have a different handler for different messages, because the data in each of them is going to be different and result in the extraction of different variables. And finally, we get to a message I'm actually going to receive, and that is filter 5, message 107. And so I'm setting that callback to handle 107 frame. Instead of just a generic handle can frame, I have a handler just for the 107 frame. Mostly to test that I'm parsing this out correctly. And if we pass all that, we're going to put on the screen that we are using can. there's some discussion about whether that should be called CAN 0, CAN 1, or CAN. But we'll get that worked out, and the initialization is completed. If it fails any of this, really if it fails the begin, we're going to print that the CAN initialization sync error. And so we'll be able to tell that we have effectively done that. Now, I talked about these handle 107 frame and handle CAN frame. Here they are, and I don't have much in them. Here we get the frame comes in. This is a pointer because we're going to be past the address of the frame from the library, and it holds in memory the actual frame. I call them frames. You might call it a form. Almost makes more sense. And in this case, all I'm going to do is if debug's on, I'm going to print the frame. And I'm going to print it as being received with, this is a sent bit. And that just lets my print function tell if it was a sent or a received frame. But I could say something like, let's see here, what would UINT 32T some CAN stuff equals frame, and I have to use a pointer because I'm getting an address. Data dot, see 32's high, and I could say UINT 16T is some other CAN stuff, and it's a 16-bit, and it equals frame data dot S0. And I could even say UINT 8T, an 8-bit unsigned integer, is yet more CAN equals frame data, and hit pointers data byte let's see, we used S0, so 0 and 1 are gone. 2. Now, if I didn't make a complete mess of that, that'll compile. And it did. So we can leave that in there. And this is how you build a extracting into these variables data from that data structure that I showed you. That's right here. And so you can see that high is the second 32 bits. S0 is the first 16 bits. And that leaves, let's see, 0, 1. 2, data byte 2 would be where S1 is. High is where S2 and S3 is. And so 2 or 3 is available to me for an 8-bit. And that's how we're going to extract data in these. And then if debug's on, we send our frame. But normally, you pull this out into local scope variables, and then you'll do some operation on them. Divide them by 10 or subtract 10,000 and divide the result by 10 to take out an offset and it's very common to scale things to handle decimal points. If I have 346.5 volts, I can't carry a decimal point in an integer, and so I can't carry it in a CAN message. But if I took 346.5 and multiply it by 10, I have 3,456, and I could carry that in a 16T, in a 16-bit unsigned integer. And on the other end, all I have to do is pull it out and divide by 10, and I've got my decimal point for the voltage. And so most of CAN is ways of taking real-world data and converting it into integers and putting it in 8 bytes. That's the deal. That's what CAN is. And so that's what we're doing. Here's my handle 107 frame. I'm just going to print, we've received a 107 frame. And then I'm going to print the frame. And I'm not, at this point, doing any extraction, but I could do all of this and more, and then do this. I can put anything in this handler that I want to. The important part is that when we pass that filter, it's going to go to handle 107 frame, and so I have to have a handle 107 frame function, and it has to be able to accept a CAN frame, actually the address of a CAN frame. And we're calling that frame here. I can call that Joey. It's the local variable I'm using in here, but we're receiving the address of the CAN frame itself that holds the data. And so that's how you do it. Now, these are not part of our loop. The only time these get called is from an interrupt from the CAN device itself, from the CAN library. And that's actually usually a hardware interrupt from the CAN chip to interrupt our microcontroller and say, hey, we got a message here. And then if it passes these filters, we pass it through. And here's the magic of CAN. We don't have to accept anything. We don't have to ever look at anything. We can set all these to empty and be looking for one message on a CAN bus that has 160 different message IDs all flying around like crazy. We're only looking for one, and so we only have to deal with one. And everybody on the bus is like that. They'll have 4 or 5 messages that they respond to, and they'll have 4 or 5 messages maybe that they send, or they may only have one that they send. Some devices don't send any. They simply get a bit of information from a sensor somewhere else and act on it. And so that's kind of a key element of CAN and why it works so well with multi-controllers is most of the CAN we don't see. Our device sees it at the controller level. In this case, our controller is in the ESP32 for CAN. It's going to be out of it for the other CAN bus, and our multi-controller won't even see it unless it passes a filter. And so this is really, I think, the heart of why CAN works so well. Here's our handlers. And now here's what they do is send the frame to print frame. It accepts the frame. Here we're sending it. Remember, this was a pointer sent in to us, and we called it frame. We can just send that to the printer because it's still a pointer. Here we accept the frame and also an integer sent. If sent is 1, we're sending the message, and if it's 0, we're not. And all I need that for is to put a preface on what I'm printing as sent or received. I do a little timing in here. Again, this last was one of our global variables up top. And I'm going to calculate a diff is the variable, and it's micros, which are about 1,000 times smaller than millis, as luck would have it, minus last. And it can be, it's not the last of this particular message, it's just the last frame printed. But this gives me some very interesting information. Our actual print statement, again, is formatted with a sprint F function. I covered that in a recent video. Here's a buffer, a character buffer of 300 characters that we set up locally. And then our text, which is message ID, and a whole series of format symbols. And all of these, this one is a 3-digit. X means print it in hex. And that's hexadecimal is what we deal with in CAN. So the last description I did of this was with an I, a lowercase I for an integer. Now here I'm going to print it in the X code, 3 digits and padded with zeros. Well, you might guess that's our message ID. And then 1, 2, 3, 4, 5, 6, 7, 8 hexadecimals, 2 digits, padded with zeros, for our frame data, our CAN data bytes. And then I've got a series of decimals, 2 digits padded with zeros, for our current time. I put a time stamp on it, and then a 6-digit decimal, and that is this diff, the time since the last one. Now, on the actual data, again, I was showing you up here how you access a frame. We're past the address of it, so I have to use a pointer. The name is frame because I kept that name here. I could have called this Joey, and it would be Joey and the pointer to ID. This doesn't matter. It doesn't have to be the same as this. I just do it to keep track. This is the name of the variable as we'll use it in here, and it's a pointer to an address which is being provided to us. Whereas this is an actual integer that's being passed in, sent. And so you can see that it's frame data bytes 2. I want to do it by data byte because we're going to print each of them separated by spaces as 8 individual bytes to the screen. And then I'm going to timestamp it with hours, minutes, seconds, and milliseconds into here. And that'll tell me when it actually was printed. And I can compare that to the last time that was received and see how often that message is coming in, or the last time we sent it. Remember, we're using the same print frame for sent messages and received messages. And then this is just a little extra sugar, a 6-digit number that is the difference in microseconds. And it'll overflow at a million or 6 digits, but it's not going to be more than a second or two, I wouldn't think, since the last time we printed. And this gives me a very fine timer that is beyond milliseconds. And if sent, if this was set to a 1, we're going to say sent. Otherwise, we're going to say received. And then we're going to send the buffer out the port, and that's how we print a frame. Here is, you'll be interested in, our way we send frames. And recall that in addition to frame, we also had another variable called the out frame. You probably want to keep them separate because you could be interrupted while you're doing this by a receive frame. And so your variable would be, so we tend to use an input and an output frame variable. And the first thing we do here is say outFrame.id equals 0x, indicating hex 707. And that's our transmission address. Our outframe length I've got set here to 8. It really isn't. We've got 0, 1, 2, that's 3, and S2 is 4, 5. So let's change that to a 5. And it doesn't matter. It will pad it out with whatever, was in the frame last. But we tend to ignore length a lot. You shouldn't, but we do. But we'll set this to 5. Extended, if it's 1, that means we're using 29-bit message IDs, and we would have a longer message ID up here, but we're using the 11-bit, and so we'll put this to 0. Outframe request, you want that to be 0. I spent the last day trying to figure out why my data wasn't going out. It's because I had RTR set to 1. I don't know why I did that. And here we're going to set some values. I'm saying if time of day is valid, recall that will be set to true if we got our local access point up and got a time mark from NIST. And if we didn't, let's don't bother with the rest of this. There's no point in putting data in there that doesn't mean anything. But if it did, this is going to be an 8-bit number, and RTC hour, I believe, returns a 16-bit integer. I'm not sure why, but RTC, recall, is our object set by the time of day class. And it has some sub-functions, publicly available exposed methods for hour, minute, second, and millisecond. And so after we have gotten our time mark, we can call RTC.hour. That doesn't go back out to NIST. It just gets it from our corrected real-time clock as a corrected value from our local machine clock. And it brings that back as a 16-bit value. It's never going to be more than 24. So I'm going to cast it into an 8-bit and store it in our 8-bit outframe data bytes. I'm going to do the same with a minute and the same with a second. Now in the case of the milliseconds, you can have up to 1,000 of them. It's a 16-bit integer, so I'm just going to use outframe data.s2, which is a 16-bit segment of our structure, to store that. And I can take it out at the other end as a 16-bit variable, because both my machines happen to use least significant byte, most significant byte order. And so 0 and 1 occupied the area of S0, and data byte 2 and 3 would occupy the area of S1. And so I'm going to skip a byte and put it in S2, and that's simply because I got room and I want to be able to deal with it using this S2 notation at both ends, which will make it easier. And then I'm going to say can send frame out frame. And out frame is what we've been building here, and now I'm going to mail it. And if debug set to true, I'm going to print it. And I'm going to print it with a 1 in the sent bit. So when we get to the printer, it's going to say sent instead of received. The rest of the program you've seen before. These are little functions to, in this case, it's based on our micros timer and doing the modulo and division math necessary to calculate milliseconds, seconds, minutes, and hours. And the only place that's used is here in our timestamp for our print frame. And so that's the whole thing. If I call it up on the monitor, we'll see. Let me stop it and scroll back up. We get our power on reset and our information, and then it says searching for River House. and it says connected to Wi-Fi River House. Here's our IP address that River House assigned us under DHCP, and our signal strength is a minus 86 dBm. And then that's getting on the access point. Now we send a UDP datagram to NIST, and if they send one back, we say success. We have a NIST time mark, NIST F1 UTC time, and here it is, down to the fraction of a second, in this case 0.227, or thereabouts. And I'm saying that because it's really fairly accurate, but it doesn't take into account the transmission time from NIST to our machine and through the local AP to us. But I can tell you from experience that's typically 50 milliseconds is where we're going to be off. I could actually just subtract 50 from that value and be even closer, but this is close enough for government work, guys. And then it says using CAN, and initialization is completed. And then we have our sent message ID, and there's the number, and here are our individual bytes, and here's our timestamp, and here's how long since last, this being our first one. It's probably just a random number. And then we say we have received a 107 frame and printed a 107 frame. And we've received another one and printed that, and we keep doing that. We're receiving a lot of 107 frames, and now all of a sudden we have time in loop, and then we have a sent message ID, and then we have time in loop 6,335 micros. And then a sent message ID and time in loop, but there's no number here. And we have received a 107 frame and a printout of the 107 frame, and then we have 6,337 micros 2. Well, that actually goes here. Time in loop is 6,337 micros, and it's the second pass through the loop. And you can see that here. It should be time in loop 6,336 here, and micros, and the third pass in the loop. But it got broken up. And this is a perfect example. If we receive a frame while we're in the act of printing, it will stop that loop and process that frame. And remember, our handler prints out, we've received a 107 frame, and does a call to print frame. And when all that's completed, it releases it back to our normal loop task, and it just keeps printing. It doesn't even know it was interrupted. And so this is a way to be able to handle CAN messages in a very timely fashion. But it's going to chop up your timing in your main loop. So, I do most time-sensitive things by interrupt, and don't put anything that's particularly time-critical in the loop itself. And so that's how you do that. Now, there's another way to do this, and that's, I'm not going to cover it today, but you can set your CAN to simply pass everything in and not have any filters and not have any masks, and instead put a thing in your loop that says check for CAN, and it goes and checks the receive buffer and sees what's in there and routes it to different handlers. And that way you're not interrupting your loop, you're doing it by a deliberate act. But I prefer to use the interrupts because they're very timely and efficient. You can get into some situations where we're interrupting one CAN message with another CAN message with another until we drive the processor crazy. This is further complicated in this particular device because it has 2 CPUs and uses FreeRTOS as a underlying task manager. So I'm not sure if we're not playing with fire here, but it, as you can see, it works very well. Here we have sent, broken. We have received a 107 frame, received message ID, and then we have message ID 707 that goes after sent. We were in the process of printing that we had sent this frame. Now we'd actually already sent it, and we were just printing that we had sent it, and that's what got interrupted. And so that's a long drawn out discussion of our code. I think this is a neat little program. We're using the wireless function of the ESP32 to go out and get on a local access point, get on the internet, get some useful data, correct our clock with it, and then transmit that over with CAN. Most things I do have to have 3 or 4 duties and functions. We're getting a lot of calls about our battery controller, about dealing with peak shaving and time of day charges from utility companies. Like they charge you 1.4 cents per minute from 11 p.m. to 6 a.m. and 75 cents a minute from 6 a.m. to 4 p.m. and something else until 11. And they want to be able to charge using the low nighttime rate and use from the battery during the expensive daytime rate. So I've done a stupid device that's ridiculously expensive. In the aggregate, to access GPS, and all I need from the GPS is the time. I don't care about the position at all. I just want to know what time it is. So I can pass that by CAN into our controller. I can replace that with our ESP32 board without having a shield because it has wireless and so forth built into it. It doesn't have GPS, but it has wireless. I can get a time mark and cut out some of the hardware. Now, ultimately, you can see where this goes. Eventually, our controllers are based on the ESP32 module. It's going to take quite a bit of software porting for that to happen. But then we can get time of day as a simply an onboard function. Although how it's going to work in that metal box, I'm not too sure on the antenna. But that's the concept anyway. And so we're working hard on our next generation of board, and that's the based on the Espressif ESP32. These are long and detailed. I like programming. Colin likes programming. A lot of us do. A lot of you all don't. So you got to kind of let me know. This is quite a bit of work to share some rather esoteric information. I suspect a number of you don't really care, but some of you might. So we're experimenting with it, particularly with this new chip. There's a growing base of people, but so far fairly limited tools, but they are growing, and we're hoping to do our part to contribute to that. And one of the things we can do better than most probably is a CAN library and description and documentation of how CAN works. And of course, we're going to need to do all that for the documentation for our ESP32 board, because the main thing that will differentiate it from $315 boards out there is that we have 2 CAN ports, and we have CAN and we know how to use them. And it's because your car or us And that's because it are belong to us because we can do can. And that's the heart of the matter. Stay with us.